So, hi everyone. I'm really excited to be here. Thanks for coming to my talk. It's really heartwarming to see so many people that are interested in protocol buffers. So, let me introduce myself. My name is Nadav Samet. I'm an engineering manager in a startup called Tubular Labs in Mountain View, California. And I'm also the author of a library called Scala PB, which makes it fun and easy to use protocol buffers in Scala. So in case you don't know, protocol buffers is a technology that Google developed that basically enables the distributed systems to exchange messages in an efficient binary format. And I created Scala PB because I wanted to have an idiomatic way to use protocol buffers in Scala, taking advantage of case classes and other things that are available in Scala to make it more pleasant to use than the Java protocol buffers. So I created this project about 4 years ago. It's on GitHub, and it's been growing in popularity ever since. But then one day, 6 months ago, a user comes to me and tells me that they want to use Scala PB, but without giving it any protocol buffers, and ask me if it's possible to do it. That sounded like a pretty crazy idea to me, because what Scala PB does is basically taking protocol buffers and generating case classes for them with serializers and deserializers. So basically telling me that they want to use Scala PB, but without giving it any protocol buffer, it's like making me that they want to make a peanut butter and jelly sandwich, but without the peanut butter. So then I calmed down and breathed a little bit and relaxed. And I figured out that there actually might be a very interesting challenge in there. Maybe instead of starting from a protocol buffer and generating case classes and serializers and deserializers, we will start from the case class. We'll think about the case class as the schema this is basically our starting point, and we'll infer the protocol buffer from the case class and not the other way around, and basically generate serializers and deserializers from the case class. So as I looked into ways to accomplish this and I researched a few ideas, I learned a lot of techniques that related to what's called the generic programming, basically processing user-provided data types, such as case classes, in a generic way. So the beauty of these techniques is that they are not specific to Scala PB or to protocol buffers, but they can be applied in any time where you want to use when you basically want to iterate over some data type that the user provides, and you want to do something for each field in a generic way, so you don't know the data type ahead of time. So what I'd like to suggest here is that maybe you try to think how what I'm showing you is relevant to the project that you're working on. Those techniques are really powerful, and once you master them, you'll be able to get the compiler to do a lot of work for you and cut down a lot of repetitive code, and that means fewer bugs and generally happier life for everyone. So let's start. I briefly told you what protocol buffers are, but let's cover it now in more detail. So protocol buffers is a language that lets you define data structures, and it also defines a particular way to serialize them. It basically defines a specific binary format, and it generates classes or code for different languages like Java, Python, C++, and also with Scala PB. And the beauty of this system is that it doesn't matter which platform or language you use. You can have like a server team writing code in one language and a client team writing code in another language. They both have access to the same protocol buffer, and they basically can just exchange messages. Here is an example of what a protocol buffer looks like. We define a message called person, and it has a first name, which is a string, a last name, which is another string, and an age, which is an integer. And every field comes with a number. So when the message gets serialized, instead of writing the field name like we do in JSON, we encode in a binary format the tag number. And this is one of the reasons why this encoding is relatively efficient. Then we use a command line tool called Protoless, which basically takes the protocol buffer and generates code to it in different languages that it supports. And Scala PB adds a SBT plugin that lets you basically generate code for Scala, and it becomes part of your development process, part of your build tool. So this is an example of of the generated code. So on the left side, we see the protocol buffer. On the right side, we see that the code that gets generated. So basically, you'll see that every field in the protocol buffer becomes a field in a case class. And there is a very important method over there, 2-byte array, that basically takes the instance that it's running on and returning an array of bytes that's representing the protocol buffer. In the companion object, we have a method called parse from, which does the opposite thing. So it basically takes the array of bytes and give you back the instance that you serialized. So let's see this in action. I start with defining a person, and it has a first name, a last name, and an age. I just put some values, and I call 2-byte array. And I also make it a vector, so the representation is a little bit nicer. And you see at the bottom, we get an array of numbers that represent the message. And we can go in the opposite direction. You see it now in the middle window, we start from the array of bytes, and we call person.parseFrom, and we get back the case class. We get basically the instance of the case class that we serialized before. So this is all what you need to know on protocol buffers. And now remember the guy that wanted to basically not write any protocol buffers, but start from the case class. So let's see what this approach can look like. First we'll just think, why would anybody want to do that at all? So one reason that somebody would not want to write a protocol buffer is that they just want to not. Some people just don't like code generation. They just get an allergic reaction when they hear about code generation. And in other environments, like protocol buffers are useful for different teams when they want to share an interface that they can see what messages are allowed and so on. But sometimes you have one project that is more monolithic, and the messages never get serialized. It's one code base that's just small, and that interoperability is not a concern. And finally, when you don't generate code, but actually your code is the schema, then you get control over the case classes. You can add your own methods to them. They don't have to extend some base class that you get from the library. You're basically in control of the code. So the approach might look like this. We start from a case class. The user just provides some simple bare bones case class, and they instantiate it, and now they want to serialize it. And of course, now they don't have the 2-byte array method defined on it, so they're kind of stuck. And our goal here in this talk is basically to help that user, give him a way to serialize his case class, no matter what it is. And we're going to see a few options to do that. So typically in those situations, when you don't have a common base class that you can use, you use the type class pattern. And basically what we have here is the message serializer type class that gets a type parameter t, which represents the message, maybe a person. And it has a 2-byte array method that would take the instance of the person and return an array of bytes. In the companion object, I define a method apply that behaves sort of like a constructor for this, but instead it's starting an implicit search for a message serializer. And this is enabling the syntax that you see on the first line in the second window, that basically when I write message serializer square brackets person, it will start an implicit search for the instance. And then I could just use this person serializer that I'm getting back, assuming I can find this implicit. And when I get it, I can use it to serialize an instance of a person. So turns out when you want to implement those message serializers, you have to write the 2-byte array method. And the 2-byte array method tends to be very repetitive. It's always the same. So what it essentially does is it's calling another abstract method called serialize size to find the size of the encoded message. And then it allocates an array of byte in that size. And then it creates something called coded output stream, which is a class that's provided by Google that knows how to write primitive fields into the array of bytes. And then you call a function called write_to, which basically takes the output stream and the message and writes the message, encodes the message into the output stream. And finally, you return the bytes. So actually, all the action is actually happening in the write_to method. This is where the interesting stuff is happening. So from now on, we're just going to focus on how would we implement the write to method in general. Option 1 is called manual definition, which basically, this is like a Bart Simpson punishment, which says if you want to have your own message serializer, you're going to have to write it yourself. So it might look like this. We're basically telling the users, we're not going to do any work for you. You're going to have to write this implicit class person serializer, and then in the write to method, you'll go field by field and send it to the output stream. What do you think about that one? It's tedious. It's error prone. It's not fun. I don't like it. It's fired. Let's move on. So second option is called the runtime reflection. So this is a very literal picture of runtime reflection that you see there. And basically, runtime reflection is a way to use the information that's available to us, in the JVM. It lets us inspect every class and list the members of it and ask the JVM like what are the types of the fields in this class and get the values of them. So the code that actually does runtime reflection tends to be a bit verbose. So I have pseudocode that kind of gives the idea of what it looks like. So the write to method here would basically go over the members of the type. Type of T would give me some type information. And basically, if the member is a string, we call output.writeString. If the member is an integer, we call output.writeInt32 and so on. But the problem is what happens if we don't have here the type that we actually got from the user. We have two options, right? We can throw an exception, or we can just ignore the type, but none of these options are good. So, and this is one of the drawbacks of this approach, that we only discover problems, for example, if the user wants to pass a datetime and we just didn't plan to, like we didn't have a way to serialize it, then it crashes at runtime. Let's just review the pros and cons of this one. So the good thing about it is that it's not manual, like the Bart Simpson punishment, right? So we get something that generates, we basically get a function that can serialize almost anything. And we have small code. It's just one function. It's just one class. It compiles really fast. On the downside, errors are getting discovered at runtime. So we get exceptions if we get at runtime when something just doesn't work as intended. And turns out it's slow, really slow. So slow that we're going to move on to the next one. The third option that I investigated is called the generic derivation. And finally, this is something that I'm really excited about. I learned about it very recently. And this is basically a way to get the compiler to create type classes for you. And it's combining 3 advanced topics beautifully together to get the effect that we want. So those concepts called HList, shapeless, generic, and inductive implicit search. Just I want to see a show of hands, like who heard of at least one of those things. I see a lot of hands, like who knows all 3 then? Cool. So I see that there are less people that know all 3, so at least I get a chance to teach something. And in just about 5 minutes from now, you'll be an expert in generic derivation. So let's start with H-lists. So Scala lists are basically homogeneous. In what sense? In the sense that if we basically, we expected to pass things of the same type when we instantiate them. So if we have a 1, 2, 3, and nil, the type infer would tell us that we have a list of integers. However, if we try to do something like this, throw like random things of different types, 42, false, foo, the compiler will tell us what is the least common denominator, and it basically says we have a list of any. So essentially, we lost the type information that we had. So enter HList that is implemented in the shapeless library, and it basically provides us an implementation of heterogeneous linked lists. And now we can define something like this, right? We import shapeless, which gives us a new meaning for the : operator. and we get basically we can compose this list like this, given different types, and at the end we put h-nil, which represents the empty heterogeneous list. And when we run this, basically the inferred type would be int : boolean : string : h-nil, which basically every type that we had in the instance actually is represented here. So we didn't lose any type information like we had in the list any before. Every type is actually captured here. Here is a quick example on how you can use it. I can define a type alias HL, assign it some type definition, define a function that accepts an instance of HL, does nothing. I mean, it throws an exception actually, and then pass an instance of that H list to my func. And the cool thing here is that if I pass an instance of an H list with the, like, that one of the type isn't right somewhere, this would just not compile. The second advanced topic is generic. And generic is a type class that knows how to convert between data types, like case classes, to their generic representation. So here is an example of what it does. So here is where I instantiate a generic of a person. And the inferred type of it is basically contains a type inside of that's called wrapper, shorthand for representation, of string int h-nil. Anybody knows why string int h-nil? Because a person has a first name, last name, which are strings, and then age, which is an int. So basically it detected the fields that the case class has, and they are represented here. And now I can use it. I can take a person, gen, called .to on it, and I'll get an H list that represents that case class, the instance of that case class. And I can now also go in the opposite direction. I can give person gen.from an H list that represents Justin Bieber. And turns out it's actually 24, which is something I learned when I prepared for this talk. This is quite an amazing fact that I think everybody in the room should know. And when I call person gen.from, I actually get Justin Bieber back out of the H list. I get an instance. So formally, this is the definition of generic. It takes a type parameter t, which is my person or the message I want to serialize, and it takes and it defines a dependent type called the wrapper, which is the representation type, normally like an H list for a case class, and it has a pair of methods to and from that would convert back and from the type to the generic representation. Inside the companion object, there is a type alias called the aux for auxiliary, which takes two type parameters, t and r, and it's basically a generic of type t with a representation type r. And this trick allows me to capture both the type and the representation type together in a single type definition. All right, and the last thing that basically holds everything together, all this approach together, is called inductive implicit search. So I don't know if a lot of people know that, but when you invoke an implicit search in Scala, it's a recursive search in a graph, and just let's see what it really does. So let's say that you define this function func that takes an x and an implicit a of type a, and you invoke it like this, func of 17. And basically this triggers at compile time an implicit search. And the compiler has these rules of where to search for implicits, and it will search in certain places for an implicit, for something that can give it this a. So it might find this function make a that returns an a, so it's a candidate for this implicit search. But this function a wants a b. So in order for this to work, the compiler has a new problem now. Now it needs to find an instance of b, and if it can find one, it will be able to use this function to create an a. So now the compiler starts a search for b, and it might find this function, make b, that wants a c. And then the compiler starts to search for a c, and let's assume that it finds this make c that doesn't want anything. So it's basically the search is stopped and is actually successful at that point, we can have a C that we can use it to build a B, to create an A, and give it and call that function. So basically what happens at compile time is that this function call becomes basically the compiler creates code that creates the implicit like that. So we basically got the compiler to solve a search problem, and we're going to manipulate this behavior to get it to build a type class for us. So before we do that, I want to introduce another type class called Field Serializer. So Field Serializer is a type class that knows how to serialize a single field, so of type H, which is the type parameter. So it basically has a method called serialize, which takes the output stream, the tag number, and the specific value, and it writes it into the output stream. And when I have this definition, I can define a few serializers. I can define the int serializer, which knows how to serialize ints, and a string serializer that knows how to serialize strings. And here's the new idea. We have a message serializer. We want to basically create a message serializer of type T. And the idea is to basically create one by converting this type T to its generic representation to some H list R, and somehow get a message serializer for this R. So if we manage to pull this off, we can easily build a message serializer of type T. We'll convert every T to an R and just use this message serializer for an R to magically serialize it, and we're done. So here's the code that does that, and it looks a little bit verbose, but basically what we have here is it's an implicit function that returns a message serializer T. And to create this message serializer T, it requires two implicits. It requires the generic that would convert my T to an R, and it wants a message serializer of an R. So if we have all of that, it is easy to create a write to function that takes a T and serialize it. We'll use the generic.to method to return an R, and we'll use the wrapper serializer, the message serializer of Rs, to serialize that H list into the stream. So for person, it would just look like this. We have a message serializer of a person, and we'll find a generic person that would convert it to this H list of string int. Remember, first name, last name, age. And we'll somehow need to get a message serializer of this H list and combine them together. We'll have the message serializer of a person. But the problem is, like, how do we get the message serializer for an H list? How can we get basically those built for us? So serializing H list, turns out it's not very hard. We just need to work in two cases, right? We have the base case and the inductive case, and this is why it's called inductive implicit search. Basically, we'll need to serialize the empty list, the HNIL thing. So it turns out that serializing an empty list is very easy. You just do nothing. So you basically have this HNIL serializer with an empty write to method, and you're done. Easy. Now our new problem is to serialize a non-empty list. So what's a non-empty list? It has a head type and a tail. And to serialize a head followed by a tail, we need a field serializer for the head. So it's some string or an integer, some type at the top of the list. And we need a message serializer for the rest of the list. If we get these two, we just combine them and we serialize the entire H list. So you'll see in the second window how you actually do that. So we have an implicit function that returns an add, a message serializer of an add followed by a tail. And the inputs that it wants a field serializer for the add to serialize the first type, and a message serializer for the tail to serialize the rest of the list. And once we have all these ingredients, we can basically call fieldSer.serialize to serialize the head, and the tail serializer to serialize the tail of the list, and we are done. So this is what actually happens, right? We want to have a message serializer of a person. Using the generic, we convert it to some H list, and we have a message serializer for the H list. And through the implicit search, we basically each time shave the top of the list and get a field serializer for that, and have a message serializer for the rest, until we have a message serializer for an empty list, which we defined. And all of this graph construction happens at compile time through implicit search. And I think it's very beautiful and elegant technique, and it actually works. And the code that gets generated is pretty efficient. So let's review that. we finally get errors at compile time. So if that case class that we're trying to serialize doesn't have contains something that we don't know how to serialize, like a UUID or something we didn't plan for, the implicit search will fail. So we'll know at compile time that that we cannot create a message serializer. The code that gets generated this way is relatively fast, much faster than reflection. And the user can provide their own custom serializers. So if the user really wants to serialize something, they can just define an implicit field serializer, and the compiler will find it at the right time, and it will just become part of the graph. So this is customizable, and that's a good thing. On the downside, unhelpful compiler errors. So it turns out that if you cannot find your field serializer, something wrong happens during the implicit search, the compiler will complain about the top level thing, about the message serializer of a person. And it wouldn't give you a lot of information about where the actual problem is. There are various ways to do that, to get the compiler to give you more verbose output, but it basically tells you, like, what it had for breakfast 2 days ago, and it's kind of hard to follow, and it takes practice to be able to understand what it tells you. Another thing that I observed is that the code this implementation that we get is slower than the generated code that Scala PB already had. And for my investigations, the reasons for that is the conversion back and forth from the case class to the H list. And also there's a lot of boxing and unboxing going on when that happens. And finally, we showed how to do encoders, but it's unclear how to do decoding. And the reason is that in protocol buffers, when you get something from another system, the field can come in any order. You're not guaranteed that they're sorted by increasing tag numbers or anything like that. Generally, they would be, but it's not. Basically, the protocol says it can come in any order. And it's a bit unclear how to efficiently create an H list when things come in an order you don't expect. So in summary, I like this method a lot. It's a great method. But because performance is something that is really, really important for Scala PB users, I continued looking into other things. And that basically made me dive into the generic type class, and I learned that it's implemented by a macro. And as I went through this, I basically found myself creating macros that would be more specific to Scala PB than the generic macro. And basically that took me to the fourth approach, which is called implicit macros. And macros have this reputation of being this black magic, this evil supernatural power that is reserved for only few Scala gurus who knows what they're doing. And I basically spent a few weeks and learned that stuff, and I can confirm that this is partly true. But at the same time, kidding aside, there is actually a lot of documentation these days and a lot of answers in Stack Overflow. And Shapeless itself is there's a lot of macros there that you can learn a few tricks and a few ideas, and there are other places. So what I want to show you here is like what it takes to write a macro. Most of the code you see is real. There's a little bit of shortcuts that I took just to make it fit the slides, but this would give you a good kind of like feel for what really it takes to write a macro. My goal is to convince you that it's not that bad. So turns out that every macro basically looks like this. It's basically an implicit function that returns the type that we want. In this case, message serializer of type T, and the body of it just says the keyword macro followed by a function where the macro is actually implemented. And this is the macro implementation. Basically, it gets this weak type tag that would give us some information at compile time on the type T, and it needs to return a tree, basically an abstract syntax tree of the Scala language. And the current implementation that you see here is just 3 question marks, so this is throwing an exception. And if I actually try to use this macro, it will throw exception inside the compiler at compile time, and the compiler would just explode. So don't do that. But you might think that basically returning a tree, an abstract syntax tree, is a hard thing, but turns out it's actually very easy. there is a technique called quasi-quotes, which basically looks like this. You write Q, and then inside this block in red, you write Scala code. And what actually happens is that this gives you back an abstract syntax tree that the compiler creates out of the code that you give. So what we have here is basically a function that returns a tree, and that tree gets injected into your code when the macro gets invoked. That is it, right? This is basically what a Scala macro does. So the code in red that we have here is basically creating an instance of a message serializer that extends the type, that basically extends message serializer of the type T, and the write to method inside is currently empty. And then we instantiate that message serializer, and this is what the user gets out of it, basically. So how would you implement the macro to actually serialize something? So the first thing we want to do is to get all the field serializers for the types that we have in our case class. So it turns out there's a very cool method called infer implicit value that I can basically tell the compiler, start an implicit search for me for the field serializers that I care about. And it will get the compiler to, basically this is the macro telling the compiler start an implicit search. And it will give me back some other tree that represents the implicit that it finds, and then I can inject that into the code. So basically what I'm defining here, this implicits, is a sequence of tree that represents instantiation of all the implicit field serializers that I want. I'm a bit cheating here with the syntax. This Q field serializer is not real syntax, but you get the idea. And then when I have the implicits, I basically generate a series of serialization statements. I basically call those implicits.serialize method, and extracting values out of the instance and passing them to the serialize method. So I basically just create this code, and then I have this syntax. I have the implicits and the writes that we just talked about, and then I can just, with a $$ notation, I can basically inject them into the code that gets generated. In practice, it looks like this, right? So this is what it would look for the person. I have a first name, which gets assigned a string serializer. I'm basically using the field name to assign a serializer to, just because it's easy. And then inside the write to, I just call those serializers to get the output written. And this is it. This is basically a macro that serializes protocol buffers. And it really doesn't take long to write. And it works really, really well. So you kind of notice that we basically closed the full circle, right? Because we wanted to avoid generating code ahead of compile time, and now instead we're generating code inside during compile time. But turns out we're also generating almost the same code that we would generate before compile time. So it has similar, performance characteristics. And this approach is very flexible, so I'd like to review it. It's fast. It's similarly fast to the generated code. I didn't get it to be exactly as fast. We'll see that in a bit, but it's pretty close. Users can still pass their own custom serializers because we're relying on the implicit search of the compiler. And turns out there's much better control over compiler errors. You can basically, with enough effort, not much effort, you can basically tell the compiler which error to give to the user. You can catch exceptions in it, and deal with them and emit compiler errors. So you can make it as friendly as you'd like. On the downside, there are limited debugging tools. So this is something that might change, over time. But as far as I know, you cannot you basically generate code, with a macro, and the users cannot see the code. They cannot put breakpoints in it, things like that, and that can be, pretty annoying for users. Right, so what I want to do next is show you the relative performance of the approaches that I showed you. So at the bottom, the black line is the baseline generated code that Scala PB already had for several years, followed by the macro approach. And the slight difference that you see there is coming from the fact that the generated code directly calling the output stream. There isn't that field serializer abstraction in the middle. But I do think that with a little bit of effort, I can get it to exactly match the line. And with the generic generic derivation, we have it's slightly slower. So I just want to basically show you how to read the graph. On the y-axis, there's time, right? How long it takes to serialize a message. The units are nanoseconds. On the right axis, we have how big the message is, right? So a bigger message takes slower to serialize. So basically, it's the number of fields that it has. And we're still talking nanoseconds here, so everything here is super fast. And this was produced with a tool called JMH, which basically lets you do benchmarking on the JVM. And it takes care of all the annoying facts like warming up the JVM and forking it multiple times to avoid pitfalls with the JIT. Where is reflection? Let's zoom out. Yeah, there it is. So it's we're talking microseconds, right? So it's still, there is a couple of orders of magnitude difference, but it's still, it's relatively fast, but not as fast as I want things to be. So basically, this is the 4 approaches that I looked into, and my conclusion is that at least for Scala PB, it looks like the macros is the winning one. But it doesn't mean that this is true for every project. I think us as software developers, we should know what's out there and pick the right tool for the right problem. And sometimes you just want to optimize for different things. What I'd like to to again remind you, those things are pretty general. So every time you want to write some code that takes a user type and does something with it, you can use that stuff to cut down boilerplate and get the compiler to work for you. So you have basically more less repetitive code and fewer bugs, fewer errors, and generally better life. So that's all I had. And no matter what your peanut butter is, you just try to find a way to cut it. Yeah. Thank you.
Thank you very much. And we still have time for questions, so let's start right away. I go there and then come back to you.
Thank you for an interesting talk. I can see it has a great value, for example, for projects where you need to temporarily serialize data and get it back. But how is there any way you thought of handling compatibility backwards and forward like we do with ordinary protobufs?
Yeah, so this is true, right? So when you get an H list and if you store it somewhere and then for long-term storage, and then the case class somehow change, you can't really get it back in a way that protocol buffers and protocol like that would give you. So basically, if you're not if you store it in a way that is not designed for schema evolution, all bets are off, right?
Thank you for a great talk. Actually, this is my first question about schema evolution, and I don't really get the answer. So far, there is no support in this generic and macro stuff, right?
Okay, so maybe I'll explain what it would look like, if and once this becomes part of Scala PB. So you start with a case class, and if you basically have some set of fields and you serialize them. And then you try to deserialize it, but in the meantime, you introduced more fields, things will get out of order. So one possible solution for that, if people want to develop with evolution in mind, with schema evolution in mind, they can use, for example, an annotation and basically write something like, put like an field tag 1 or something like that. And then the macro can find that stuff and basically always use that tag number for the field. So then they can kind of guarantee over time that the schema.
So there are plans to introduce schema evolution support.
Specifically for protocol buffers, that's definitely necessary.
Okay, then second question was about in Scala you can have silly traits and abstract data types.
Yeah.
Is there a automatic derivation for those? Because in protobuf you have one-off semantic.
Right. So yeah, that would be necessary for enums and one-offs. And of course, that would be part of it. I didn't want to go into core products in this talk, but it's definitely going to be part of what we'll have at the end.
So it's there are plans to implement this also, right?
Yep.
And is this on GitHub?
Not yet. It's basically work in progress. That's kind of like private for now.
And when can we expect it?
Well, that's a great question. So
maybe community can help.
Of course, yeah. So one of the things I learned in my career is that when I'm asked for estimates in public, I'm trying to avoid giving them, especially when the video is recorded. So so it's gonna come in the future.
Yeah. Okay. Thank you.
We heard about all the problems with future promises. And so, yeah. Thank you for your talk. Is it possible to use this technique to also get an IDL back from your case classes? So maybe because I realized in the future, oh, now I need to share my data structures, and instead of hand writing them down based on the case classes, I would like to have it generated via, I don't know, a compiler switch or something like that, and then share this with some other people in the company or with the outside world.
Yeah, fantastic question. I think this is actually an application that you can easily do, right? We're writing a type class that would get you a protocol buffer schema as a string out of it, and you'll basically iterate over the fields. You'll know the types and basically transform that. I think that should be very, very doable.
You make me earn my lunch.
Yeah. What about schema evaluation when you have several schemas and you want to evolve your protocol buffer schema to another version?
What is exactly the question then?
Do you plan to manage schema evaluation with generated code?
Yeah, so basically, in this approach, when you add fields to the case class, you'll have to somehow mark the tag numbers if you really want the messages to work, like to be able to parse data that was serialized in a previous version of it. So if you introduce tag numbers, what happens is that when the message gets serialized, the tag number is written to the output. So as long as the new version of the after the evolution, right, the new version of your case class has the same tag numbers that that had in the original one, the fields that were in the right slot, the field from the original one would just get into the right slot into the new one, and fields that you removed would just get dropped. So that would take care of that.